In this video, I'm going to roll out an introduction to Computer Assignment 1, which should be posted online already. The idea behind Computer Assignment 1 is that you're going to uncompress some audio that I've compressed down for you using a pretty low budget compression method. Here's how it works. Let's say we've got an audio clip that is, I don't know, some duration in time. It doesn't matter how long. So any audio clip will have something called a sampling rate, FS, and that is the number of samples per second. And a very common sampling frequency, sampling rate for audio is 44,100 samples per second. Okay, so what that means is that you can imagine a list of numbers, sample number 1, sample number 2, sample number 3, and so on. And at some point, you'll get to the 44,100th sample, and that will be 1 second worth of audio. And every second of audio is another 44,100 samples. So that is what uncompressed audio looks like. And what you can imagine is that with 44,100 samples per second, it adds up quickly, right? If you have a few minutes or a few hours of audio, that number of samples just adds up like crazy. So what we have is a compression algorithm. So here's what I've done. What I'm going to do is I'm going to start by analyzing the first 20 milliseconds of audio. Okay, so the first 20 milliseconds, let's see if it's 44,100 samples per second. If it's 44,000, samples per second times 20 milliseconds, that comes out to 882 samples. So the first, what we're going to call window, is 882 samples long. Okay, so that'll be window 1. And then there's going to be a window 2. Right, window 2 will be the next set of samples. So sample 883 all the way up to 2 8 to 16, up to sample 1766. Okay. Nope, my math is not good. 1764. Is that better? There we go. So that'll be window 2, and so on. Right? There's just going to be a series of these windows. So what I'm doing, I'm going to take the first 20 milliseconds, the first 882 samples, and I'm going to analyze them. And it doesn't matter for your purposes how I did that, but I did an analysis. And in the analysis, I work out which are the 15 strongest cosines represented in that signal. Sorry, not the 15, the 50 strongest cosines represented in that signal. So what I'm going to yield for window 1 is 50 frequencies. So you can imagine a list of frequencies. Let's say it's like 73 hertz and 412 hertz and 972 hertz and so on, right? There's going to be 50 frequencies, and correspondingly there's going to be 50 magnitudes and 50 phases. So really what that means is, let's say this was 2.7 and this was I don't know, minus pi over 8. What that would mean is that the first cosine is 2.7 cosine 2 pi 73t minus pi over 8. And then, of course, there'd be another cosine that corresponded to the second one and another cosine that corresponds to the third one. There would be 50 of them in all. Okay? So essentially what I'm saying is that that first window, that first 20 milliseconds can be represented by a sum of 50 cosines. And I'm telling you the frequency, the magnitude, and the phase of each one. Well, that just gets you the first 20 milliseconds. What about for the second 20 milliseconds? Well, for window 2, you're going to do the same thing, right? You're going to take the next, took the next 882 samples, and from those, I extracted the most prominent 50 frequencies, magnitudes, and phases. Okay, so there's 50 of those for the second window. And of course, since there's different sound going on in the second window than in the first window, you would expect that there's going to be 50 different cosines, right? So different frequencies, magnitudes, and phases. So for each 20 millisecond window, we're going to yield what is effectively 150 numbers, right? Each 20 millisecond, 882 sample window is going to be compressed down to how many numbers? It's going to be compressed down to 50 frequencies, 50 magnitudes, and 50 phases. So it's going to be compressed to 150 numbers. So that's a lot of compression, right? If you wanted to figure out, boy, I can't spell numbers today. Let's try that again. If you wanted to figure out what our compression ratio is, you could figure out, well, we started with 882, we ended up with 150. So what does that divide out to? And that leaves us with, let's pull up the calculator here, 150 divided by 882, that's about 17%. Okay, so we've reduced our original signal down to 17% of the original, that's some pretty good compression. And because it's a lot of compression and it's a low budget style of compression, you can imagine that it's not going to sound all that great. Okay, but it doesn't matter if it doesn't sound great. We're learning. Okay, so what you're going to do, so that's the compression method, and then we're going to repeat this process for as many windows as we have in the audio. Okay, so repeat until end of signal. So that's how I compressed the audio. So your job is to uncompress the audio. So here's what you're going to do. You're going to go to MATLAB. You're going to open a editor window. Make a file called, doesn't matter, right? Call it something.m. And you're going to start putting your commands in. The first command is going to be something like load audio 1.mat. Actually, your first command is going to be clear. You should never start anything without clearing the memory first. And then if you were to look to see what's loaded in memory at that point, you would find three variables. There's the sampling frequency, which is loaded for you. You don't need to redefine that. That has the value of 44,100. There's going to be a variable called frequency in hertz, and that is going to have the dimensions of 651 rows by 50 columns. And there's going to be a matrix called A, which also has the same dimensions, 651, comma 50. Okay? And A is the complex representation of magnitude and phase, right? We learned earlier that that your magnitude is, sorry, that your variable A is your magnitude over 2 e to the j phase, right? So effectively, it's one complex number that stores two variables in it. It stores the magnitude and the phase. So that's what I'm going to do here. I'm going to store both of those. I'm going to store the magnitude and the phase in the complex A. All right. So if you want to know the magnitude, you can just say magnitude equals the absolute value of A. And you can say phase equals the angle of A, right? So those are built-in MATLAB commands that will give you the magnitude and the phase. Actually, technically, the magnitude is going to be 2 times the absolute value of A in order to account for that 2 over there. Great. Okay, so what is the 651? All right, what's that all about? So the 651 is the number of windows. And right off the bat, we can use that to get a feeling of how much audio we're dealing with. So if we had 651 windows, and we know that it's 20 milliseconds per window, then we should be able to estimate that the total audio is going to be 651 windows times 20 milliseconds per window is going to give us 13.02 seconds. So when we're done, that's how long our audio should be. And if we want to know what the duration of the output signal is in terms of samples instead of in terms of seconds, we know that the equivalent of the 20 milliseconds is 800 and what do we say? 882 samples per window. That's samples, which corresponds to, let's see, 651 times 882, which equals, am I doing that in my head or on the calculator? Let's do that on the calculator. That's going to come out to 651 times 882, gives me 574,182 samples. So that's what your job is, right? Your job is to figure out the values of those samples. How are you going to do that? Well, I'm glad you asked. So here's the final product that we're trying to attempt to rebuild. And instead of worrying about all 574,182 samples, let's just start by worrying about samples 1, 2, 3, up to 882. Let's just deal with window number 1 first. Okay, so window 1 can be recreated as follows. For window number 1, if, actually let me redraw. This is the 651 by 50. Okay, so this is a graphical representation of the frequency in Hertz matrix and the A matrix. So what you can imagine is that the first window is going to be the first row of, of that matrix. So that's going to be window 1. So, and that's got 50 numbers in it. So there's going to be 50 frequency in Hertz, and there's going to be 50 values of A. So what you're going to do is, you're going to say for window 1 is going to equal, like this. So window 1 is going to equal magnitude cosine 2 pi ft plus phase, where the frequency is going to come from the frequency in Hertz matrix, and that will be the first cosine from the first window. So that will be 1, 1, right? The first window, comma, first harmonic. And then same thing, you'll get the magnitude and the phase in a similar fashion. Okay, those will come from the A matrix. And then you're going to add to that m cosine 2 pi ft plus phase. But this time, you're no longer using the first of those 50 cosines. Now you'll be using the, let's use green. Now you'll be using the second one of those 50 cosines, right? So now you'll be doing frequency in Hertz of first row, second column, and so on. And you'll go on down the list until you've summed up all 50. Okay, until you've worked your way through all 50 of the cosines that are represented in the frequency in Hertz and A matrices. And all that work will yield you the cosine for window 1. Okay, now what do you do after that? Now it's time to move on to window 2. Okay, so in order to get window 2, you're going to do the same exact process. It's going to be a sum of 50 cosines, but now instead of working from the first row, you'll be working from the second row. Okay, and then again, the columns will iterate from 1 to 50. And then you go to do window 3, and you'll be working on the third row. Okay, so you're going to go work your way down through all 651 windows until you've completed the entire thing. So for each case, you're going to be summing together 50 cosines, and then you have to do something with that. You have to take, so first of all, let's talk about how big that is. You know that this has to be 882 samples long. And the only way to do that is to make sure that your time vector is also 882 samples long, right? If your time vector is 882 samples, then your cosine will be 882 samples. And then when you add together all these different cosines, you'll just keep adding, you'll add together it'll automatically add for you all the first elements, all the second elements, all the third elements, all 882 elements. So you generate those time vectors, and then you're going to take whatever your sum is, and you're just going to make sure that you put it into the final signal. So maybe you want to call your final signal something clever like X. You want to make sure the first window gets parked in X samples 1 to 882. And you want to make sure the second window gets put in the next 882 samples. So that'll be 883 through 1764. That'll be window 2, and so on. Okay? And you're just going to keep going down the list. Easy as that. All right. So let's see. Do I have some parting thoughts for you? Oh, how will you know you've done it right? So one of the ways you'll know you've done it right is you can play the audio signal. There's a built-in command in MATLAB called sound SC, which is short for scale. And you're going to take whatever your signal is, X, and you can do sound XC, X comma sampling frequency, and you'd better hear about 13 seconds of audio. Okay, so that's one way to check. All right, that's probably the easiest way to check. What else did I wanted to say? Oh, a couple things. I wanted to say, let's talk about the time vector real quick. In general, when you create time vectors, the easiest way to do it, let's say you want to make 1,000 samples of time. 1,000 samples of time. The easiest way to do that is to say, look, give me a vector from 1 to 1,000, right? So 1, 2, 3, 4, all the way up to 1,000. Now, if you leave it like that, what that suggests is that you have a sample at t equals 1 second, a sample at t equals 2 seconds, and so on, all the way up to a sample at t equals 1,000 seconds, right? Which is clearly nuts. That doesn't make any sense because we know that there's 44,100 samples per second. So 1,000 samples is not 1,000 seconds, right? 1,000 samples is, just a tiny fraction of a second. So the way to account for that is to divide that by 44,100. Okay, so if you do that, each of those 1,000 samples will get divided by the appropriate number, 44,100, and then that way you'll find out that your final sample is 1,000 divided by 44,100, which comes out to about 2.3 milliseconds. Okay, so that'll be about 2.3 milliseconds. Okay, which makes sense, right? If you have 1,000 samples, you have about 2 milliseconds of audio. 20, I was off by a decimal point, not 2.3. That's about 22.6 milliseconds of audio. All right. So that's one way to do it. This is essentially the number of samples, and then this adjusts to make each sample represent the correct amount of time. Another way you could do it in general, let's say you wanted to make 3 seconds of audio. You would do it like this. T equals, again, we're going to go from 1 all the way up to our final number. Now, how do we know how many samples to make? If I want 3 seconds, is it 1,000? Is it 2,000? Is it more than that? The easiest way to do it is to say I want 3 times 44,100. Okay, and that way it's going to automatically figure out how many samples I need to get 3 seconds worth of audio. And then once again, I divide that down by 44,100. And in that manner, my final sample will correspond to 3 seconds, and I'll have the right number of samples with the right spacing and so on. So in general, that's how you create your time vectors. You get the exact correct sampling frequency that way, which is exactly what we want. All right, now here's the final piece of the puzzle for the computer assignment. We did this project so far by taking the original audio signal and breaking it into 20 millisecond windows. So why 20 milliseconds? What makes 20 milliseconds special? And what we're going to do is I've effectively uh, done the compression 2 more times, but instead of using 20 millisecond windows, I'm using 100 millisecond windows and 500 millisecond windows. So the first thing off the bat, you can imagine that if the windows are bigger, there's going to be fewer windows. And in fact, you're going to see exactly that. When you open up the audio, when you open up the data files, you'll see that instead of having 651 windows, you're going to have about one fifth that number for the 100 millisecond and one fifth again for the 500 millisecond windows. So the number of windows is going to go down, and that shouldn't be surprising. But I want you to take essentially once you've built the little program to rebuild your signal, it should be fairly easy to modify it to take account different window sizes. And you're going to rebuild the second two signals with the different window sizes. And keep in mind they correspond to the same original audio signal. They can sound very different when you put them back together. They might sound better, they might sound worse. I don't want to give away the answer. What I'm really interested in you doing is reconstructing those other two audio signals, and then deciding for yourself what kind of effect the window width has on the processing. I want you to be able to say, for example, 20 milliseconds was the best, 20 milliseconds was the worst, whatever. And then I want you to give me a rationale. Why does that make sense? Right? Why should you have been able to know that was the answer, even without having done the math or anything? There should be some reason why it came out the way it did, and I want you to try to apply some reasoning to explain why that is. All right. So in order to make that easier to do, in order to make the doing the window lengths, the change window lengths a little easier, I wanted to give you one more tip, and that is the easiest way to do this is with a series of loops. So for example, you could write a loop that says for I equals 1 to 651, meaning repeat the following commands for once per window. And then within each window, you could say for j equals 1 to 50. Okay, and then so essentially you're saying do the following once for each window, once for each frequency within that window, and then add them all up or what have you. So this is essentially the shell. You're going to put a bunch of code in different places to make it work. And that's fine, but one thing that you should always avoid is hard coding in numbers like 651 and 50. And the reason is, what if you come along now and then the numbers change? It's not 651 anymore. What if I give you a different window size or a different length audio signal and 651 isn't correct anymore? You really don't want to have to go back and keep changing your code every time. So the way we're going to handle that is before we start, further up in our code, we're going to put in a command like this. So we're going to say number of windows, comma, number of frequencies equals size of A. So A is that A is 651 by 50 matrix we were talking about. And if you write this command, then automatically n windows will be assigned the value of 651, and number of frequencies will be assigned the value of 50. So if you do that, you no longer have to write I equals 1 to 651 over here. You can write I equals 1 to the number of windows. You can make that a variable. And you can do the same thing here. You can say j equals 1 to number of frequencies. I guess just frequencies. So there's two advantages of doing that. First advantage is what I already said. If the size of your A matrix changes, you don't really have to change your code at all. The other advantage is it makes your code more readable, right? If someone comes along and looks at your code, they might look at the 651 and say, I don't understand what the 651 is. But if they look at n windows, they're going to know that that means the number of windows. You've made your code easier to understand, and that's something you should always aspire to. Okay, well, hopefully this works. When you're done, you should hear a 13-second quote from a movie that you may or may not recognize. But even if you don't recognize it, you should hear a man's voice speaking. And if you have any questions, you can either email me directly at iobaid@temple.edu, or you can send me an email through Canvas. So good luck and get to work. I wouldn't save this until the last minute.